Financial crime in the age of AI, how connected intelligence enables real-time detection. I'm your presenter, Victor Lee. I'm the head of product marketing here at TigerGraph, and I've been here in a variety of roles. So I've sort of developed a good knowledge of graphs and the graph databases. So talking about financial crime today, which is been going on probably as long as there have been transactions. But what's different about it these days is the way technology is making it happen. Both our transactions are happening faster, and of course, fraud is happening faster. So 7% of every dollar in credit card transactions is lost to fraud. And it's a huge problem. $40 billion currently and growing every year. And it's 1.5 million transactions per minute because those are digital transactions. There are real physical customers swiping their cards in stores, but it's also people using doing transactions on their computers, on their phones, and there are even pre-scheduled ones where it's just happening automatically. And that's where fraud can easily creep in. Because if you think about it, if you can conduct your transactions electronically, so can the fraudsters. And not only are they doing it by they used to have to write code to make up hack the systems or take the information that had been stolen and construct what look like real identities. But now they can use AI tools and just say a few lines and ask the tool, hey, the equivalent of Alexa or, of Siri, make some fake identities for me based on this set of identities that I've bought on the dark web. And they contain parts of real information and they look really good. So you can do photos if you need photos with deep fake technology. Very easy to create, numeric and name documents. And then they use the same technology to look at, hey, what do legitimate transactions look like? What do we know about how banks are trying to detect them? And make some fake transactions that look real. So pattern mimicry and automatic layering. Layering when you're doing money laundering of spreading out the money, structuring, you know, taking the ill-gotten funds and putting it through a series of transactions, which individually look benign, but what's actually happening is they're washing the money by having it run through the system. And it can use AI to create very legitimate looking phishing. So you've probably noticed that you used to get these phishing attempts that looked really corny and they were pretty easy to spot. And now it's very hard to tell that they are fake. And you have to go by the rules of don't download anything, don't install anything that you were not expecting, that you didn't ask for. Um, Check the hyperlinks to see, don't just read the visible text, but read the hyperlink to see is that actually the company that you think it is. So there is so much, the AI technology is creating very realistic looking, but fake transactions and identities, and it's doing it faster than people could do it. So, what do banks have to do? So, the industry, the advisors, the research institutes, the banks themselves, they're saying this is what we have to do. We have to do behavioral analysis. You can't just look at the transactions individually. You have to look at, well, who is making that transaction, when, why, what else are they doing? What are they doing over time? You have to look at behavior. So that's forming a pattern. You have to look across time. You have to look at what an entire account is doing, what an entire person is doing, who are they connected to, where is the money going, and then what is that other account doing? And whenever possible, institutions have to share information because money gets sent from bank one to bank two. Bank one has some of the information, bank two has some of the other. And while, privacy matters, but they have to find ways to combine their information and connect it all. And you have to monitor continually and adapt as you see new patterns, and you have to be able to respond quickly. The thing is, all these things they're recommending, it's what TigerGraph has been recommending already before AI. And the banks that worked with us on their fraud detection, they were able to increase their fraud detection rates by 20% even before the age of AI. What the ask is now, keep doing that, but think even bigger. N Go beyond what you were doing. You have to connect even more things. So it's finding hidden connections and patterns. Not just looking at individual transactions, but saying what is the chain and what is the breadth? What is the shape of that behavior, both in shape and over time, how it evolves? What is the overall structure? When different institutions share their information, then you can see, oh, okay, money went from here to that other one, and that other one, it's sent to there. Then when you stitch it all together, you can see how the money was being layered and that this is clearly money laundering. So it's it's more of the same techniques that if you were not using graph before, you need to be using graph now. So, as I said, what we've been able to do is help financial institutions increase their fraud detection by an average of 20%, some more, 300% increased efficiency in fraud case investigations, and AI is going to help that even more. So, depending on the size of the institution, that 20% could be worth $100 million dollars or more. And because of our scalability, we're able to take very large data sets. And I said, with the AI, you're going to have to look broader and deeper. And so the data sets are going to grow. And so the need to be able to scale and to still perform at scale is going to become even more important. Even though the analysis is very big, the reaction time needs to be real time. So with some institutions, I'll go over a use case right here where the requirement was to be able to respond very, very quickly. So JP Morgan, $50 million dollars in savings each year due to the improved fraud detection. So they are the largest credit card issuer in the United States. They invest heavily in the best technology. And a few years ago, they saw that they needed to invest in Graph to improve their capability. They get 50 million transactions a day. And due to the fact that, again, these are digital transactions where customers expect rapid approval, 80 milliseconds to make a judgment. Is this fraudulent or not? Do we block it or not? So they had 30 terabytes of data. Again, they have tens of millions of customers, tens of millions of credit cards, millions of merchants that they work with. Each of those have to be part of the data set that's being analyzed. So the solution, and we'll go over an example later, a demonstration, using machine learning algorithms, graph algorithms to generate features which are used to train machine learning algorithm. And the graph features improve the quality of information going into the machine learning. So quality in, quality out. And that is the theme for how graph helps, whether it is with traditional analytics, whether it's with machine learning, whether it's with AI, is the quality of the insight you get from graph improves the quality of the results you get out. Another institution, Nubank, the largest bank in Latin America, operating in multiple countries. They were getting a large number of scam reports. They're getting complaints from their own customers. They're having, losses of their own account, approximately $2 million a month. So tens of $1 million a year. And in their case, the biggest problem was so-called mule accounts for, again, more like money laundering, where a fake account is set up. It's like or it's a real account, but the access to it has been stolen, and somebody is making use of your account to pass funds through. And so they were not able to do a very good job of detection until they started using Tiger Graph. Again, once again, using graph algorithms, calculating up to 30 graph features. When I say a feature, what I mean is calculating some characteristic about your data. And these, because they're graph, they're going to be pattern based. So some pattern based characteristic of your data becomes another information piece that they use to train the machine learning. And again, so they have 65 million accounts. Again, very large bank. And this is basically cut where they were had 60% false positive. That dropped to like 30%. The recall, 28%, jumped up to over 50%. So a lot fewer errors, catching a lot more of the actual fraud. And again, so those are two big success stories, had other success stories. So this is a very effective method and it's very transferable to other organizations. And as we said, in the age of AI, it's actually the same technique you should be using. It's just the data that you gather. If you weren't looking across time, you need to do it. If you were not connecting as much information before, you need to do it. And you need to set up a very efficient real-time system. Once you decide to adopt AI, that can help your organization in additional ways. You can use it not just in the detection phase, but in the investigation phase. So once a suspicious situation is detected, so there's some fraud that you stop on the spot, and there's other activity that is more, there is a fraudulent business per se, or an organization, and you are trying to shut down the organization. And you're not just trying to stop individual transactions, but you're trying to shut down the operations. So you need to do an investigation. And there can be clues, and the AI can suggest what you should look at. It can make it the investigator doesn't need to write code. They can simply talk to the AI agent, and the AI agent can help generate reports. So, as I said, it can be doing monitoring for you and suggesting actions. There's also compliance issues. And so the AI can both help, as using agentic AI, can help to implement compliance features, and it can make suggestions for where things need to be changed or improved in order to stay in compliance. And lastly, as we suggested here, while it can assist investigators, it can assist both the institution's employees and assist customers in other ways. Give you helpful advice. So once you decide to adopt AI, you can help the institution in multiple ways. And graph, again, gives the value of graph, as we'll see, gives you more context to improve the quality of your AI. Large language models, which are the core of the current generation of generative AI, are wonderful, but they're not perfect. They still have their limitations. Like traditional machine learning models, what you do is you give it a lot of training data, and where it sees the pattern, it sees how, for example, in the case of human language, it sees how people tend to talk. It's a statistical process. It's called generative because it takes those statistical patterns it sees to create new examples. It generates new language, new sentences based on patterns it's seen in the past. However, like a lot of machine learning, neural networks, it's not very explainable because it's sort of it's using all these um, embedding vectors that aren't you can't break them down and say what the different parts of the vector mean. That's why graph makes a great complement. Graph is giving exact deterministic relationships. It says this person has this account, not this person probably has this account because I've looked at people in the past in their situation and they usually have this account. No, you're saying this person has this account. Fact. So they make a great complement. So information that like these are the compliance rules. These are our account types that we offer. These are the specific limits. These are the transactions that this customer has made. They give you a much stronger foundation. They give you context. And because they're based on relationships, they can explain things much better than a statistical model. And so, what we can do today is what you were able to do in the past. You would take your structured information, information that was sitting in your relational database, in your tables, and you could think it approach it a little bit differently and represent it as entities and relationships and make a structured graph. But what you can do today with LLMs is you can use the LLM's ability to take your documents, your news reports, your financial reports, economic reports, fraud alerts, things that are written in human language. They're not in just in tables. They're paragraphs. But the LLMs, because they recognize language, they can take that apart and they can find the entities and relationships and still build a graph, as well as preserving the original text for reference and using that as examples. So you have your structured text, you have your unstructured data. You can make this complex hybrid graph, which is very rich, a hybrid knowledge graph, which is going to help for reasoning and decision making. Now, how does this all help AI? It fits in here where when a question is being asked, it looks at the things in the question and it says, what is related to that? If for you mentioned this person, you mentioned this account, you mentioned this concept. Search your knowledge base to say, what do you know that is relevant to that? And send it back to enrich the search. This enrichment is called RAG, retrieval augmented generation. But when you're using a knowledge graph, that is the most powerful kind because it's using this very rich relationships, not just sort of flat vectors which only look at similarity, but not similarity is not the only important type of relationship. There's, uh, parent-child, ownership, location relationships, all sorts of time relationships that are enriched because you're using a graph structure. And again, the theme, quality in, what we've done here is we've made the information here better so that when you do send it to the LM, you're going to get a more relevant, more accurate response. How TigerGraph is helping to enable GraphRag is by uplifting our existing scalable high performance graph database to make it a hybrid graph plus vector database. Vector, the key to storing embeddings and vector similarity, one of the foundational elements in the current generation of generative AI, as well as good old graph, entity relationship to give you discrete, deterministic, explainable, meaningful AI with our high performance engine. So both parts, both the graph and the vector, have the performance and scalability that TigerGraph has become known for. And because in this workflow, you need to talk to the graph, you need to do vector search to find things that are similar. Going from the question to find things in the graph, there's actually a similarity search as the first step because it's in the same product. You're cutting down on communication, your time, you're cutting down on maintenance, having to maintain two separate products. So using the TireGraph scalable hybrid graph database is a great way to implement this graph RAG, which is elevating the quality of AI and the AI that both if the if the fraudsters, if the bad actors are using AI, the the good guys, the financial institutions, the retailers need to also be using AI, but using graph AI to get the best results. And with that, I want to show you an example of some of those use cases we took, how TigerGraph does fraud detection. So we have in our cloud offering, TigerGraph Savannah, our TigerGraph as a service. It offers these solution kits. We have nine solution kits in three categories, with the biggest being financial crime. And one of those kits is transaction fraud. What the kits include, they include a graphical user interface, a graph model, queries, and sample data. And in the case of this one, it also includes a machine learning notebook because this is using graph plus machine learning to achieve its end. So I'm going to walk through actually our transaction fraud solution kit. So having these kits really accelerate your ability to go to develop a working solution so that instead of having to develop all this from scratch, we already have a reference example with some automation so that you can get something up and running in just hours or days. So with that, I'm gonna switch displays. And so this is the dashboard that comes with the transaction fraud solution kit. And this is representative of what a financial institution, a bank, might have in their credit card fraud detection business. So they have operations where they're developing machine learning to try to detect fraud. And the things that they care about are some of these statistical measures. Two very important ones are precision and recall, because they are making basically a yes no decision, fraud or not, block this transaction or not. When you're doing that type of predictive work, you have precision, which is the number of, in this case, positive predictions, transactions, which are they decide, they predict are fraud, the percentage of the ones that they claim are fraud that actually are fraud. It's like, how often did you get it right in that sense? There are a couple different ways, subtle differences between talking about the different judgments. Recall is how much of the actual fraud did you catch? So looking at these numbers, these are representative of these are this is somewhat synthetic data used in our example, but it's representative of what we saw from our customers. So initially, before they were using the graph, they're getting about 62% recall, which means they're catching 62% of the fraud, and about 54% precision. That means when they claim something is fraud, they're right about 54% of the time. And there's this is week by week, it's varying, but this is about typical. False positives and false negatives. This is another measure. This is looking at, again, another way of looking at was your prediction right or not. And again, in this case, you want the false. False means you predicted wrong. You'd like these numbers to be down at zero. You'd like these numbers to be up at 100. So these numbers you'd like to be higher, these numbers you'd like to be lower. And if the particular institution can say, based on our long-term average or looking at the actual transactions, how much did each error cost us? When there's fraud, remember I said at the beginning, 7% of every dollar is lost in fraud. And depending on the type of business, how large their transactions tend to be, that'll have a certain dollar effect. In this model, we assumed that each false negative, every time you missed catching fraud, it cost $200. And we said every false positive, when you incorrectly claim something as fraud, it costs $50. Why does it cost you money? There is some administrative work if the customer files a complaint, initially gets corrected. Um, you've also rejected business. You've rejected legitimate business. And so there's opportunity costs there. And there's reputational loss because if you make these false accusations too much, your customers are going to be unhappy with you. You're going to lose business. So, the blue down here, it's sort of pretty smooth where that's the false negative cost when you miss fraud. Interestingly, the false positives, when you incorrectly claim something as fraud, it costs more. And even though they don't do it very often, it's because of the balance between how much fraud. Only 1 out of 1,000 transactions typically is fraud, and so a lot more of them are not fraud. And so even getting a small percentage of them of wrong is large in absolute numbers. So I spent a lot of time explaining all that to you, but because I want you to really understand the business side of fraud detection. And again, for this hypothetical bank, it's costing them this week $6.27 million, the previous week 8.33. It's going up and down. So now, what does TyGraph do? So where TyGraph comes in, first we said there's a graph model. So through our experience of working with lots of banks, we've seen that this is the type of data they typically have, and these are the type of relationships that matter. First, here, this represents a transaction, a payment transaction. It occurs at a certain time and it's for a certain amount. And then there are these other properties, which are actually things that we compute along the way. So the first few are things that are known, that are given to us as data. The rest are things that are derived during the analytics. Another key part is the merchant. So these are credit card transactions. There is a merchant. Again, there is, and this second property is PageRank. Some of you may recognize that as a common graph algorithm because part of the analytics we're going to do is we're going to compute a PageRank score for the merchants. Um, Over here is the party. This is the consumer side of the credit card transaction. Again, there's an ID, there's a prediction of whether it's fraudulent or not. And there's some biographical information. But interestingly, there's actually a lot. All of these other nodes are also demographic or biographical or behavioral information about the party. So some of it is stored with the node, but some of it is stored as other properties, excuse me, as other nodes. And the reason why you do that, there's a graph way of thinking. If there's a characteristic where you want to compare to see if do other people have this in common, it helps to think of it as a node. And lastly, because these are credit cards, this is the card. Um, and again, this ID, is it fraudulent or not? That's a prediction we're going to make later. There's a PageRank score again, and there's some other characteristics. And some of these others are things that we again do to break down the data or come up with the analytics. But these four here are the key core, the transaction itself, the merchant, the party, and the card. And of course, how are they connected? How are they related to one another? So they have their traditional tabular data and they bring it into the graph. And tyGraph has a very efficient system for ingesting this data in bulk. So once you have the data, then what do? Then you want to run some graph queries, graph algorithms. tyGraph includes a graph data science library with over 50 algorithms. The first one we're going to take a quick look at is in the community category, and it's called Louvain. And some of you may have heard of Louvain before. It's a pretty well-known algorithm for finding communities in a graph. And in this sense, what I mean by that is these set of individuals interact with one another relatively often compared to interaction with others. They interact enough that we decide these form a identifiable cluster. And what this algorithm does is it looks at the activity to decide where those community boundaries are. There's the only clue is the interaction. There's no other clue. It's based purely on interaction. So this is written in GSQL, our query language. So the thing is, um, if you need to customize this algorithm, you actually can because this is just GSQL, which is our user-facing language. This is one of our standard algorithms in our library. This is this is going to be key. A lot of the other analytics we're going to do are going to depend on this community. So you can think of this one as a first step. First, you identify the communities, and then we'll do some other calculations. Uh, Centrality, we talked about PageRank before. Very common algorithm. Interestingly, the core that is about. Let's see, that's the input, that's the output. That's the core of PageRank. The rest of this is for input and output handling. So it's actually a pretty simple algorithm. But again, one of many in our library, and we're actually going to compute it twice, once for the merchants and another time for the cards. In addition to these standard library algorithms, we also have some custom queries, which are specific to the use case. And there are, again, about 20 or 30 of these. We'll just look at one of them. This one's called Community Transaction Average Amount. Now, remember, we looked at Louvain first. Louvain finds communities. So now that you know what the communities are, like, for example, let's say, okay, these 20 nodes belong to one community. So I'm not looking at the entire graph. I'm just looking at those 20. What is the average transaction amount? That's what this query is doing. This query is saying for each and every community, compute what its average transaction amount is. And why? Because it turns out that if there's fraud, that this number may fall in a certain range, or it may be higher than average or lower than average. What the thing about machine learning is we don't know in advance what is the signal. We just know that this might be useful information. And so we give it to the machine learning algorithm to tell us, hey, I found out by looking at all the use cases that if this is 20% higher than average, that is a clue that is one additive factor to make it more likely that this is fraud. And the idea is that when you combine all the features, when you combine all the 30 features, whatever, in a certain balance, that the machine learning algorithm will be able to make a very accurate prediction of fraud. And it's the idea that Graph is adding all these features that you would not have had if you weren't using Graph. And Graph is looking at how things are connected. It's not looking at just at the transaction. In this case, it's looking at a community of transactions. It's doing comparative analysis. So that's a very powerful technique. So the last part we're going to look at is the machine learning notebook, which is Python. It's a Python notebook, which you can actually add documentation to, like images like this. And this image is, excuse me, here to explain the workflow. And this is a very typical machine learning workflow. You have input data. From that, as I said, you generate features. Features are characteristics of the data which may be useful, such as that average transaction amount per community. That's a feature. Some of these are already, you just read straight off the data. Some you have to do some computation, like running that community average transaction amount in order to derive the feature. The thing is, this is the traditional path where you don't have your data structured as a graph. We still use that. The banks are still using a lot of their traditional features, but You take some of the data, you form the graph that we showed. You form a graph like this. Um, and then you run some of those algorithms that we mentioned. And you generate additional features. So now you have your traditional non-graph features plus your graph features. You can now do the same type of machine learning model that you did before, but it's the fact that you have richer, more meaningful information that you therefore get better quality results out. So, we're not going to try to teach you Python or XGBoost here. I'm just going to sort of look at some of the headings to sort of see how this is organized by section. You connect to your tygraph database because the database here, machine learning is typically run on another server, so you have to connect the servers. Um, there was actually another script that actually ran the algorithms to extract all the features. So we're assuming that the features are already there, but now we're taking the features and we're collecting them as a set and sending them. So we're actually building the data set that the particular machine learning will work with. Some of those features were non-numeric, so we do a translation into numeric values. Um, now, so you have a full set of data. Now, this is training data. Training data means that we actually already know which ones are fraudulent and non-fraudulent. The whole idea is we're giving it examples to look at. We're saying here are 1 million transactions. A certain portion of them were fraudulent, and we know that, and we've labeled them as fraudulent. And what we want the ML model to do is try to figure out the pattern of the features that are predictive, that are associated with the ones that are fraudulent. So now we have to split up our data into two or more sets, use this set for training and this set to test if our model is working well or not. Um, and then it turns out we're using XGBoost, which some of you may know. And it's once you've got everything set up, it's actually very simple to just call it, and it generates a model. And then again, remember I said there's a training set and then there's a test set, so we test it. And then we run the model again. So we actually created two sets of features. One set that includes the graph features, and another set that does not include the graph features, so that we can compare. And this chart is showing the comparison. It's showing how the precision improved when we included graph and the recall improved. And remember, these are the characteristics that you would like to be 100%. So we went from 40 to 82 on precision, and we went from 54 to 89 on recall. So significant increase. Again, this is an example. This is, excuse me, results will vary depending with different customers, different data, but those are representative examples. And lastly, we'll go back to our dashboard. This was looking at a certain slice of time. Um, this is through August 2nd, 2025. We're going to update, excuse me. So this is 10 weeks later. We're assuming in that the graph model was adopted on that August 2nd date, and that it's taken a little bit of time for it to take benefit to see the effect. And so now we're seeing the effect. And we're seeing how precision recall, excuse me, are growing towards getting closer and closer to 100%. And we're seeing how the false positive and false negative rate is dropping. And most importantly, to the bottom line, the cost of fraud is going down. The the amount of false negative cost is going down, but probably more importantly, the false negatives when they were incorrectly targeting, saying that a transaction was fraudulent. So, it may be surprising to know that it's actually when they get it wrong in the sense of saying this transaction was fraud when it wasn't, that actually tends to cost more. But again, you can see the significant drop. Again, results vary every week, but it still hasn't maybe stabilized, but it's definitely clearly dropping. We went from $6.27 million 10 weeks ago to now only 1.4 million that week. So thank you for sitting through with that demo. I know it took a little while, but hopefully it was interesting. So let's just wrap up. So, the value of why you want to use a graph to help with your fraud detection, particularly with AI, is because it models relationships and it enables you to see the patterns. And it's the patterns and how things are related that are the key. If you're using a native graph database, it's going to be much more efficient to analyze relationships than trying to use some other type of database. You also get with it, and if you get a graph database like TigerGraph, it includes a graph algorithm library. So you can run Louvain, so you can run PageRank. And as we talked about graph RAG, you can also add it to your AI pipeline to improve the quality of your AI results. TigerGraph in particular, we have worked with lots of the world's largest banks, as well as smaller ones, all sizes, to help them reduce their fraud. We have an algorithm library, as we talked about. It's full range. It's written in GSQL, so the algorithms can be customized. And probably, of course, the experience and the enterprise quality of our product is very important. But why did they pick us? It's because of the scale and performance that we were designed massively parallel processing as a distributed database, the ability to process these, and for several customers to do their workloads in under 100 milliseconds. And finally, in the latest incarnation of TigerGraph, you have the hybrid graph plus vector capability, which is going to deliver amazing results for graph RAG and AI. And so, when applied to trying to do real-time fraud detection, graph is connecting the data from multiple heterogeneous sources, structured and unstructured. It's uncovering these sophisticated, in some cases, AI-generated fraud patterns, and the product itself, the graph, can integrate easily with AI and machine learning to integrate them. So, I want to thank you very much for your